Okay, so starting with number 1, I just start the algorithm like normal. So if I'm at my start state and I see a blink, then I want to just move to the right and then transition into a state that I named move 1. Okay, so if I'm at move 1 and I see a 1, then I just want to keep moving right because I'm not trying to change the ones. I'm trying to replace the blinks. So, okay, so I'm at my move 1 and I see a blink. Move 1 will sort of like represent the first blink that I see. So okay, so move 1, I see a blink, then I go ahead and replace that blink with the 1, and then I keep moving to the right because I want to add one more 1 to the end of the string, and I transition into my move 2 state. So I'm at move 2 and I see a blink and I replace that blink with the 1, and move 2 will represent the second blink. So I know that after that second blink is replaced with the 1, then I want to go ahead and start going back to the beginning of the tape. So I'll go to the left and then transition into back. And then if I'm at my back state and I see a 1, then I know that I haven't reached the beginning of the tape, so I keep moving to the left. And then if I'm at my back state and I see a blank, then I just go ahead and halt. And then for the tracing, so my input is 1, and I know I want to come out with a 3 in unary form. So I'll start at the beginning, the blank, so I transition to the right and transition into my move 1 state, and then I'll keep going until I reach the first blank, and then from there I see that move 1. If I see a blank, then I go ahead and replace it with a 1, and then I move to the right again and I'll transition into move 2, and I know if I see a blank in move 2, then I replace that blank with the 1, and then after that I just move to the left and transition into the back state, and then keep going left until I'm at back and I see a 1. So if I'm at my back state and I see a 1, and then I just halt. Okay, so starting with number 2, I know that in my string I want to replace that blank that represents a plus sign with a 1, and then I know that I want to replace the very last one with a blank, just so it outputs the correct answer. So working with 1 blank 1 1, I know it represents 1 plus 2, and obviously that's 3. And so if I replace that plus sign with a 1, that'll get me just 4 in unary, but obviously that's not right. So I want to go ahead and replace the very last one with a blank, so that'll get me 3 in unary. So 1 1 1. Okay, and then so I just start like normal. So if I'm at my start state and I see a blank, then I just move to the right and then I transition into a move state. If I'm at my move state and I see a 1, then I just keep moving to the right because I don't want to do anything with those ones, with the very first ones. So if I'm at my move state and I see a blank, then I just go ahead and so if I'm in my move state and I see a blank, then I know that blank represents my my plus sign, so I go ahead and replace it with a 1 and then keep moving to the right, but transition into a state that I named first. So in my first state, if I see a 1, I just keep moving to the right. So basically, I'm trying to reach the end of the string so I can go back 1 and replace that very last one in the string with a blank. So okay, so now if I'm at my first state and I see a blank, then I know I've reached the end and I want to go back 1 and transition into my second state, or into a state that I called second. So if I'm at my state called second and I see a 1, I know that's the very last one and I replace it with a blank. And then yeah, so I go back to the left and transition into a state called back. And then if I'm at my back state and I see 1, then I keep moving to the left until I reach my state back where I see a blank state. Then I know I've reached the beginning of my tape and I go ahead and halt. And with the tracing, I did the same thing as 1, so I move to the right until I see the first blank, and then that first blank, or not the first blank, it's technically the second blank in the tape, so I go ahead and replace that second blank with the first, not with, well, yeah, transition into the first state and then replace it with the 1. And then I keep going until I reach the next blank. So I know I've reached the very end of the string, so I go back 1, replace that number 1 with a blank, and then I just go back until I reach the very beginning of the tape, and then I halt. So that just outputs the 1 1 1, which is correct. Okay, so number 3, the first thing to notice is or that I did was find a pattern between the input and the output. So in the input, I noticed that it was the exact same or almost the same as what was in the output, except that in the output the numbers would be shifted down, and then in the first position, or I guess technically in the second position after the blank, there would be a 0 that represents the least significant bit. So yeah, so 0, and then it would be the exact same as what, after that 0 would be the exact same as what was in the input. So yeah, in my algorithm, I knew that I had to keep track of what was in the current position, so that the next position, when we move to the right, it could be replaced by what was there, by what was in the last position. So again, I was just like shifting the numbers down after I replaced the first one with a 0. So okay, so in my start state, if I see a blank, then I just want to move to the right and then transition into a state called move. And then if I'm in my move state and I see a 0, then I don't want to replace it, since the first one is already supposed to be a 0. So I just want to move to the right and then transition into a state that I named replace 0. And it's kind of like to keep track of what was before. So since I saw 0, I'm transitioning into a replace 0 state. And then if I'm at my move and I see a 1, then I know I want to replace that 1 with a 0, because again, the first digit should be a 0, or I guess technically the last 0, the last digit when it's like in the correct order. So if the first position after the blank holds a 1, then I know I want to replace it with the 0. And then I want to move to the right and go into my state that I've named replace 1. So again, this is just to keep track of what was before. So okay, so if I'm at my replace 1 and I see if I'm at my replace 0 and I see a 1, that means I want to replace that 1 with a 0 and then move to the right. And then since there used to be a 1 there, then I want to go ahead and transition to a state that I named replace 1. So if I'm at my replace 0 and I see a 0, then it doesn't have to be replaced. So I just move to the right, and then I stay in my transition. I stay in my state replace 0. Okay, so if I'm at my replace 1 and I see a 0, then I want to go ahead and replace that 0 with a 1, and then keep moving to the right. And then since there was a 0 there, then I want to transition into my state named replace 0. And then, okay, so if I'm at my replace 1 and I see a 1, I don't replace it since there's already a 1 there. And I move to the right and I stay in that state named replace 1. Replace 1, I see a blank, then I know I've reached the end, and I go ahead and replace that blank with a 1. And then after that 1 is replaced, or that blank is replaced, then I go ahead and move to the left and transition into my back state. So if I'm at my back state and I see a 0 or 1, it doesn't matter. I go to the left until I reach that state back where I see a blank. And then I go ahead and halt. So tracing n, and this is if n equals 4. My my input is blank 0, 0, 1, and then I just added a blank. So if I'm at my start state and I see a blank, then I move to the right. If I see a 0, then I know that 0 should stay. But I know the next one has to be replaced by a 0 if it's not already a 0. So in this case, it is a 0, so it stays the same. And I know that since I'm at my replace 0 state, I know that the next one, that one has to be replaced by a 0 since I'm at my replace 0. So that one that I see here needs to be replaced by a 0. So now I have blank 0, 0, 0, and then since I'm at my replace state, since I'm at my replace 1 state and there's a blank, I know that blank needs to turn into a 1. And then after that, I just move to the left. Since I've reached the end, I just move to the left until I reach the very first blank, and then I go ahead and halt. Okay, so for number 4, this is basically just checking to see if the least significant bit holds a 0 or a 1, because all multiples of 2 hold a 0 at the least significant bit. So since the least significant bit is stored at the very front, we just have to check that first digit, whether to see if it's a 0 or 1. So in my starting state, seeing a blink and then moving to the right, I'm gonna transition to a move state. So if I'm at a move state, and I see a 0, then I'll just accept it, and if I see a 1, then I'll just reject it. And then tracing the string representing 4, so in the tape it's 0, 0, 1. I'll go ahead and move to the transition to the move state. So since I see a 0 there in the move state, then I'll just go ahead and accept it. And then if n is equal to 5, then I'll go ahead and since there's a 1 in the least significant bit, then I'll just go ahead and reject it right away. And that's for 5. Okay, so explaining number 5 real quick. I just wrote that a feasible algorithm can, or is an algorithm that can run its time in polynomial time, so it can't go past that. So if it's given an input size of like a reasonable length, then it can go ahead and create, it can go ahead and complete its task within a reasonable amount of time. But I wrote that it's not a perfect definition, because you can give it an input size of an unreasonable input size, and that could still run in polynomial time, but it's no longer efficient. So it's not really a feasible algorithm anymore, because feasible algorithms should be efficient. Okay, so starting with 6, I constructed the NFA for this one, and the first line in my algorithm, I wrote if I'm in my start state and I see a blank, then I'll just move to the right, and then I'll transition to S. And I wrote S because S is the starting state in the NFA. Okay, so now for the next part, I focused on all the transitions coming out of S and where they led into. So for example, if I'm in my S state and I saw a plus sign, that plus sign led into I. So in my algorithm, I'll obviously write that, like, if I see a plus sign, I'll move to the right, and then I'll transition to state I. And then I did the same thing for the negative sign. So if I see a negative sign and I'm in state S, then I'll go ahead and move to the right, and then I'll transition to I. But for 0 and 1, if I see 0 and 1, then I'll go ahead and end up in F. And again, this is all according to my NFA. And then I did that same thing for I, F, and K. And for K, since it's a sync state, then I just it didn't transition anywhere but itself, because obviously a sync state will just transition back to itself. And then the last 4 lines, I wrote that if I'm in S and I see a blank state, then I'll reject it. same for I, and same for K. So I did that because in my NFA, the S, I, and K are not accept states. So that's why it's rejected, because if the string that I'm tracing, for example, ends up in either one of these, then it's not accepted. So the only one that it is accepted is obviously F. So that's the only one that is accepted. And then tracing the input string plus 0 and 1, I just go ahead and follow the algorithm. So if I see a start, if I'm in start and I see a blank, then I'll transition to S. If I see a plus in my S, then I'll transition to I and move to the right every single time, of course. So if I'm in I and I see a 0, then I'll move to the right, and then I'll transition to F. If I see a 1, then okay, my algorithm tells me to move right, and then stay in F. And then if I see an F, of course, and if I'm in F and I see a blank, then I'll just go ahead and accept it. Okay, so 7. I basically wrote for all of them that they're categories in which we classify problems, and that they all contain a set of problems. So NP is basically, so it contains a set of problems that all the solutions to these problems are basically proved to be actual solutions because of the fact that they run in polynomial time. So because of the fact that they are bounded by polynomial time, they are NP solutions, or NP problems. Okay, and then P is very similar to NP. So I just wrote it's a category which contains a set of problems that can run its task in polynomial time. So since it's believed to be a subset of NP, but it's not proven, that's why their definitions are like so similar. And then NP complete is just both NP and NP hard, and then NP hard is just those problems that can be translated into NP problems in order to find a solution for them. So, and then number 8, question number 8 is asking what the Turing thesis is, and I wrote it's a calculation that is produced by a computation device, so like a physical thing. So and then just saying that that calculation can also be produced by a Turing machine or any other computing machine. And again, it's not mathematical because of the fact that it can be or more like that it depends on this computational device. So it depends on something from the physical world.